One of the most intriguing results from this paper is how poorly multimodal large language models, or MLLMs, handle identifying the same object attributes across different camera views. For instance, they struggle to spot that a red shirt on a person in one view is the same as in another, almost like trying to recognize a friend in a crowd from a totally different angle without any hints.
That's a great point, Ben. To achieve this result, the researchers created the All Angles Bench, which is basically a testing ground with multiple camera perspectives of the same scene. They designed tasks where models have to match attributes, like colors or shapes, across views. Think of it as piecing together a puzzle from scattered photos. Each piece shows the same picture, but from a different angle, and the model has to figure out how they connect without getting confused by overlaps or occlusions.
Building on that, another fascinating outcome is the model's trouble with object manipulation across views. For example, if a person in one view starts moving an object, the MLLMs can't reliably predict or track that action in another view, making it seem like they're watching separate movies instead of the same event.
Exactly, and the method behind this involves crafting questions that simulate real-world scenarios, like asking the model to describe an object's path as it moves between views. It's similar to directing traffic in a busy intersection. You need to keep track of multiple paths and ensure everything aligns, but these models often lose the thread when views don't perfectly overlap, highlighting their weakness in maintaining geometric consistency.
Then there's the challenge with relative direction and distance. The paper shows that MLLMs frequently misjudge how objects relate to each other across views, such as figuring out who's standing closest to a certain spot in one camera and spotting that same person in another.
Right, to test this, the benchmark uses questions that require the model to compare positions, like estimating if something is to the left or right relative to another object. Imagine navigating a room with your eyes closed, relying on memory from different doorways. It's tough because you have to mentally map everything out, and that's what these models are failing at when views don't line up perfectly.
And let's not forget camera pose estimation, which turned out to be a big weak spot. Models can't easily sort or reorder views, like figuring out if they're in clockwise order from a top-down perspective, showing they're not great at understanding the overall layout of a scene.
Absolutely. The process here involves shuffling views and asking the model to reconstruct the sequence, much like trying to reassemble a broken mirror to see the full reflection. This tests their ability to infer camera positions and orientations, but it reveals that MLLMs lack the intuitive 3D awareness humans have, especially with partial occlusions, where parts of the scene are hidden.
Overall, these results paint a picture of MLLMs as impressive for high-level tasks, but still clumsy in multi-view scenarios, particularly when dealing with occlusions or mismatched perspectives.
To wrap it up, the key takeaway is that while MLLMs are advancing quickly, they need better ways to handle multi-view understanding for real-world applications like navigation or manipulation. This benchmark highlights the gap and suggests we might need specialized tweaks, like adding modules that mimic how humans build mental 3D maps, to bridge it and make these models more reliable embodied agents.